So again, the COSLA again, they considered that the flow below the impermeable base of hydraulic structure, they considered the flow dynamics beneath the hydraulic structure in order to be able to calculate uplift pressures. Basically, they considered groundwater, saturated groundwater flow conditions beneath. Finally, the water seeping below the hydraulic structure does not follow the bottom of the profile of the impervious flow stated by Bly, but each particle traces its path along a series of streamlines. We shall see what we mean by that. And I think that one we will see, yeah, I can already show it already here. Because now that one is, yes, that point really directly relates to determination of exit gradient. So what we are saying is the water seeping below does not follow the bottom of the profile, but follows a path, kind of a streamline, follows a path from the upstream to the downstream. So that is what that point means. So now, because of that, COSLA developed a method that is called method of independent variables, whereby the structure, because it is complex, remember it is a structure that is constructed as a monolithic structure. It is massive and it has joint. It has a wall, it has a slope, it has piles, sheet piles, and what have you. So we have, if you could break this, it has a flow. So if you could break this structure, you can easily break it into components. But for purposes of improving the resistance to uplift pressures, it is constructed as a monolithic structure in order to create bending moment kind of situations. So what he did is he divided the structure. He divided the structure into components. Let me see if the image. Yeah, so that now, if you have a structure like this, first of all, you cut this section, upstream section alone, and then analyze it separately. Then the middle section with an intermediate pile, and also now lastly, the downstream pile separately. And then finally, he also, in order to do this independent, analysis, he assumes a negligible flow thickness, which is not true because we know the flow has to have a thickness T. So for purposes of initially analyzing, he assumes a negligible thickness. So in order now to add the case where you have a thickness, he also now has a fourth kind of analysis whereby you have a suppressed flow in order to add a flow. Yeah, so those are the independent variables. I think we have four of them. And let us see them. Is one of the independent variable is a straight horizontal flow of negligible thickness with a sheet pile at the upstream end. This is this case. Then we have the case with a downstream, a pile at a downstream, an intermediate pile, and then a suppressed flow, a straight horizontal depressed flow, but with no vertical cutoff at all. And he analyzed the structure in order to determine percentage pressure variation from the upstream to the downstream. For example, at the point E1, at the point D1, at the point C1, at the point E, at the point D, at the point C, at the point E in the intermediate pile C and D, and also at the point D, that is the bottom of a depressed flow. So in this case, in the case of depressed flow, what he has done, there is no piles in the structure, but purely a depressed flow. For starters, in the upstream, the uplift pressures are maximum because that is where we have the highest hydraulic gradient. As the water flows, remember it encounters friction, energy losses, mechanical energy losses, and what have you, mostly due to friction, due to inhibition to flow, due to the permeability of the soil. So as the water flows downstream, you're going to have uplift pressures decreasing until you have zero. We expect that we are going to have zero uplift pressures as the water exits in the downstream part, exists in the downstream part after the pile. So in the upstream part, the pressures are 100% of the calculatable value. That is where the hydraulic head is maximum. It is minimum at the exit. So all these points you see indicated here, E1, C1, ECD, D1, EC for the intermediate, and then D for the suppressed flow, depressed flow. Expressions were developed in order to determine them. Secondly, in addition to those pressures that I've just indicated, percentage pressures where they are calculated, the second thing that he did was to calculate the exit gradient. Remember, with Bly's and Lenz theory, there is no provision for calculating exit gradient. And the results, the results of those computations have also been presented in a diagram, but first of all, let us see the expressions. So in the case with a straight horizontal flow of negligible thickness with a sheet pile either in the upstream end, this is the expression. In the downstream end, this is the expression. Phi E1 is 100. Phi D1 is calculated by 100 divided by pi cos inverse 1 minus that, and what have you. Now, one thing to note is when you look at the flow of water beneath is not linear, but rather it is kind of parabolic, it's kind of spheric or something like that. And because of that, the calculation is done in radians. So that when we are using our calculators, you have to set the calculator in radians, not just normal degrees. And lambda is given by this expression, and where lambda is B over D. What is B over D? Let's see whether B is there. B is the entire length of the weir. And when we are talking about B, the entire length of the weir starts from the upstream point all the way to the downstream point. That is the B. So phi C first, phi C in the sheet pile in the downstream is 0. Phi C is 0. Phi E is calculated using this formula again in radians. And you can easily correlate now the pressures in the upstream, these pressures, with the pressures in the downstream using this formula also. Now, in the case of intermediate piles, is a similar kind of analysis is applied and the formulas are given. And finally, the case for depressed flow. Now, they solved, Koestler and his team solved all this, made a solution of all these equations, and they were able to develop curves that can be, instead of going through the calculations, you can just read from the curves. And what is that seepage pressure the ratio of residual seepage head and total seepage head at key points. For example, in this case, we have the depressed flow. But it is not depressed flow alone. We have phi E, phi D, phi C1, phi D1, the upstream. This is the case of upstream piles and downstream piles and depressed flow. So how do you read it? You calculate 1 over alpha. You calculate alpha, get the reciprocal. Once you get it, then depending on what you are calculating, you will come to, let's say, for example, you are calculating phi E, phi D, and phi E, phi D. All these are the configurations. Upstream, pile in the upstream, pile in the downstream, pile in the case of a depressed flow. So in the case of upstream, downstream piles, you use phi E, phi D, and then you use this relationship up here. This relationship up here to get phi C1, phi D1. Then, so once you have calculated that value, all you need now is to draw a vertical line from whatever value you have calculated of phi D. Whatever value you have calculated of phi D, let's say you come to that point and read horizontally, read your value horizontally and do delete. And then you read your value horizontally of your, residual pressure at whatever point you are calculating the pressure. I've repeated the same down here, and in this down one, I've added the phi C and phi D curves for intermediate piles, and the calculation is still the same. On the right hand side you have phi D, on the other side you have phi C. And then you have values of alpha. Starting from, calculated as provided in the equation. Okay, so that is it. And then we also have a small form, another table here for, which is usually, this one becomes critical when we are calculating exit gradient. And you will notice one thing, 1 over pi root r root lambda. No, that one we'll see it when we come to the exit gradient. So let us just go slowly. So now, the assumptions that were made, and like I have said, the assumptions were made, negligible flow thickness, blah, 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 and such kind of things. We know in reality that is not the case. So some corrections had to be done. One of the corrections was for, of course, more realistic conditions are, we expect more, some of the more realistic conditions are that the flow raft with sheet piles at either end has a flow thickness. That cannot be considered negligible compared to sheet pile depths. And then the flow raft may have sheet piles both at the upstream as well as the downstream ends, which might interfere with one another. For example, the way we have used when in calculating or illustrating Bly's theory, it has 3 piles. So you are going to have you are going to have more than one pile. You cannot have just one in the upstream, one in the middle, and then one in the downstream. So you may find a situation whereby you have to combine more than one of those conditions. So in that case, then those piles are expected to interfere with each other. Then finally, the flow of a modern barrage is not horizontal throughout. You are going to get around the crest area, we have maybe a vertical wall or a sloping wall, depending on whichever kind of configuration the person has chosen. What are we talking about in that one? You see here, the assumption is that the wall is vertical, the water is vertical. So let me see whether I'm going to get an example here. No, it must be in the first one, unfortunately. But hopefully we are going to come across it, something in some of the examples, so that I can be able, and if I remember, I'll mention it. So now corrections had to be done for those conditions. And one of the corrections is correction for flow thickness. So how do you do it? For example, if you have a sheet pile in the upstream, we have what we have done, we have calculated pressure at the top, and I'm seeing my network is not very stable. You will let me know. So you have calculated E and C. Of course, in the figure, we have called it E1, C1 for purposes of differentiating it from the downstream one, so EC. But essentially, what we want to calculate is the pressure at the joint of the pile with the bottom of the floor on both sides. So if we call that E prime, that, pressure that below E, we call it E prime, and pressure below C, we call it C prime. So the calculated pressure at that point, one, we have to be cognizant of how fluid flows. And if I'm to ask a question to that, I know we are together. Anthony Odima. In what direction or what controls flow of fluids? What causes flow? What controls what causes fluids to flow?
Sorry.
What causes or what controls flow of fluids?
Pressure, maybe.
Yes, it is pressure. It is pressure. You are very right. But to state it differently, it is mechanical energy. You have to have an energy. And then I don't know whether we are going to talk about Newton's first law or Newton's second law. Because of that energy, when it has energy, the energy of a fluid at a particular point will propel it to move forwards. And now, if it is controlled by, let us call it pressure, let us call it energy. That energy is usually controlled by the Bernoulli equation. It has three terms: potential energy, elastic energy, kinetic energy, and what have you. But that is not necessary. But that energy, you can convert it into energy potential, all pressure, and in pressure you can write the pressure in terms of hydraulic head. A column of a fluid, for example, column of water, column of mercury, and that is now where the pressure comes in. Pressure is just one form of the energy. When you divide the energy by density of the fluid by acceleration due to gravity, you get a hydraulic head in terms, in short, you get a pressure. So that is very correct, Anthony. So another question, and I will ask, I can see, I don't know whether Bill Clinton can speak or Brian Bisonga, so I'll ask Brian Cheruiyot. Fluids, if you see water flowing from an upstream side to a downstream side, where do we usually have the high pressure, or where is the high energy? So let us say, and let me just try to draw something. Let's say we have this water flowing from here to the downstream here. So the water started from, the direction of flow is from point A and to point B. And the direction of flow is that direction I've shown. Which side do we have higher pressure? That is Brian Cheruiyot.
Everywhere in the fluid flow.
Brian, speak louder.
I thought the pressure is always constant everywhere.
Hydraulic head is. Okay, okay, then let's now talk about energy, therefore. Pressure is constant only when we have hydrostatic conditions, remember? And the question is, do we have hydrostatic conditions from point A to point B? But now let us talk about energy. If we have flow from A to B, and the water is flowing, it cannot be the same. It cannot be the same.
I think it's point.
Yes, Nyaga?
Yes, Nyaga.
Nyaga usikiki.
Nyaga usikiki.
Okay, Brian,
Okay,
you can
Brian,
finish.
you can finish.
Because Nyaga, Amanda,
underground.
I think it's point.
Yeah, one of you to speak and the other one to mute. Okay. So in the interest of time, because you have started the class late, we know that the pressure is going to start from point A. Now, in this case of the pile in the upstream side, during the analysis, during the derivation of those expressions, we assume that the negligible flow thickness is at the top of the slab. So we add a flow thickness. So if we now think about the direction of flow of the water, we are going to have flow of the water in the downstream part. So the energy E, the pressure at E, so during correction, we have already calculated this, but we want to correct for this. And we are going to calculate a certain fraction of a pressure. Which of these two is supposed to have higher pressure? So already from the expressions, we have calculated, from our expressions, we have already calculated this one. So from our expressions, we have calculated this one. Then we make a correction of whatever value, and we now want to calculate E. Which one is going to be bigger? Sorry, the correction, is it going to be positive or negative? Because the direction of water flow is in a downward direction. I'm asking a question. So we have calculated using the expressions before E. Then we are using this formula, and I will explain it a little bit. We calculate a certain correction, a value. That value we calculate, is it supposed to be subtracted from E or added? Because now, essentially, if the water was to flow, it is going to flow vertically downwards. And let me say we are supposed now to minus, we subtract from E so that we can get E prime. And then in this case, we are going to add, we are supposed to add a correction. So how do we correct? Oh, yes. Hey. Mzuri. Mzuri. Yes. Yes. Confuse number. Yes. That is someone who has really insisted on calling me from morning, who is not part of I don't know them. So that is the correction. And how do we do it? First of all, you get the difference of pressure between the points E and points D, the total, pressure from points E and points D. And then, you kind of doing apportioning pressure by pro rata basis. So you are saying if the pressure from point E to D varies, from a distance D plus the thickness T, then what will be the pressure difference between at the thickness T? What will be the pressure difference at the thickness T? So it's like apportioning through pro rata basis, and then you minus it from phi E. Then you minus it from phi E so that you can get phi E prime. And for phi C, do the same, and then phi C prime is supposed to be an addition. Phi D minus phi C, phi E minus A. If you subtract phi C minus phi D, you see now in this case we have phi D minus phi C, you still subtract it. Otherwise, if you got phi C minus phi D, you are supposed to add it. Now, so that is it. That is it for correction for flow thickness. We have correction for mutual interference, and we have an expression for that. C is equals to plus minus 19 D plus D divided by B square root of D B prime. And all those are indicated where B prime is the difference between the two piles whereby you are calculating the interference. Now, again, if a pile you are correcting for a pressure in the upstream side, you are supposed to add the correction. If you are correcting for a pile in the downstream, you minus the correction. Finally, is a correction for thickness of flow. No, slope of flow. But still, we do not have a slope. Yeah, here we have one. So the slope of flow, this is it. So you notice how this one looks like. At that point, at this particular point, the flow or the pile itself is not even a continuous mass of concrete. Otherwise, you would need a lot of mass and it would be too costly. So you just make a flow that is landing, and then of course at this point, at this particular point, you have done a lot of backfilling in order to be able to create the crest. So when you're correcting for the slope of flow, it is only applied on this particular part. For example, on this particular part, on the side, and it is only applied on the side of the sloping floor. So you do not apply it on this other side. If you had a pile here, you would only apply it on this particular point alone. In this case, you would apply, if you had a pile here, you would also apply correction for this kind of a thing. And so it can be either at the end, starting of the slope, or at the end of the slope. For a down slope, the correction is negative, and for an upslope, the correction is positive. And the calculation of the correction is as follows. First, you have to calculate the slope itself, and various slopes are associated with corrections CS. Of course, if you are not given, you can always calculate it using that formula that is given, but you can always even also now read your values from this table. Then finally, with COSLA, you have to calculate the exit gradient. And in order to do that, I want us to consider this image, which is like I indicated, saturated groundwater flow conditions beneath the structure. Now, this kind of flow is controlled by the Darcy equation, the Laplace form of the Darcy equation. Here, of course, I've indicated three-dimensional flow. Groundwater, flow of water in the subsurface is in 3 dimensions, but in this case, we are interested in the vertical and horizontal directions. And for the y direction, we assume a unit thickness of the weir. We are assuming in this a unit thickness of the weir so that this term can be ignored. So we assume 2-dimensional flow in the x direction, that is upstream, downstream, and then vertical, that is seepage as the water flows downwards. Now, those two, that Laplace application of the Darcy equation, once solved, produces a network. You are able to produce a network of streamlines and equipotential lines. And did I teach you hydrology 1? Probably not. If I didn't, and we didn't come across groundwater, in the Darcy equation, we have what we call hydraulic conductivity, or in soil mechanics, it is often called permeability. So basically, this equation is the Darcy equation, the Darcy law, and in this phi, in this potential, inside there we have hydraulic conductivity, we have hydraulic head and what have you. So the flow potential here is KH. K is a constant, so in this equation it would occur outside the differential operator. So it would be K d squared H dx squared plus K d squared H dz squared. And so when you solve those two equations, you get a network of streamlines and equipotential lines. What are streamlines? The path of flow. What are equipotential lines? Equipotential lines are lines with equal energy potential. So that along each equipotential line, the hydraulic head is the same. If you were to install piezometers, you get the same kind of pressure in those lines. Now, if you have come across the concept of flow nets, maybe in water resources engineering, what we have here is some kind of a flow net. And that is what a flow net is usually formed when you solve the Darcy law that we have just seen. And the first streamline, when we are making flow nets, is assumed to start, from the upstream and follow as much as possible the profile of the bottom of the weir. And it kind of acts as the same kind of the creep path, the path that the water follows as it creeps through beneath the weir. When you are drawing flow nets, you are able to establish the number of streamlines and the number of equipotential lines. We will not go into details about that because it's a little bit lengthy, but basically just understand that, and if you have come across it, just bring that concept of flow nets here. So let us now look a little bit about the potential equipotential lines. When we consider about the equipotential lines, Now we can come to what was it Brian Cheriot or Anthony who said that pressure everywhere is equal. And if you consider the water level at that point at the bottom of this reservoir, then we can say the hydraulic head is the same. At the bottom here, then the potential, the equipotential is also going to be the same here. The hydraulic head is going to be the same. Okay, sorry. If you get at that point, you get at that point, you get at that point. So long as you have an hydrostatic condition, the hydraulic head is going to be the same. The energy is going to be the same. And if you measure it in terms of H, and if you were to take the downstream elevation as a datum, then your hydraulic head or the equipotential or the energy is going to be equal to the height of the water at that point. And it is going to be constant all the way. As the water flows, the line, equipotential line now, varies downstream so that water can be able to, flow. And you can see it is kind of in a cyclic direction. And you are going to get, therefore, such kind of lines, equipotential lines and what have you. You can see this equipotential line here, whereby some piezometers have been installed just to show that for equipotential lines, the water the energy, the hydraulic head has to be the same. So that is how it varies. And until you get to the downstream, when the water now emerges in the downstream part, the energy, the hydraulic head is equal to atmospheric pressure, and we usually take it as 0. So in the upstream, the hydraulic head is maximum, it's equal to the depth of water or the elevation of the water. In the downstream, it is minimum, you can say it is equal to 0. Of course, if you take the datum to be mean sea level, the equipotential head at point D will be, you have to add the altitude of that area and also add the altitude in the upstream part. So, the hydraulic head calculation, you can play around with the gravity term of the Bernoulli equation by setting your own datum, So you notice as the water then flows from the upstream, there's equipotential drop. There is loss of energy. There's loss of energy. Otherwise, if there was not loss of energy, then there would be no flow of water from the upstream into the downstream. So if you look at now, as that water therefore moves, because of that equipotential lines, we are going to have water flowing from the upstream to the downstream. And as that water seeps now, you are going to find that it is going to exert a certain pressure. We are going to have some pressure, force exerted at each point in the direction of flow, If we are to linearize the streamlines that we have just seen above for purposes of illustration, for purposes of calculation, at any given point in the path of flow, that water is going to have a force. For example, you can say which is in the direction, of F, a direction of F. And this force is going to have both an horizontal and a vertical component. That is one. And then two, the particle weight will try to place the soil particles beneath are going to try as much as possible to remain in place so long as their weight exceeds the force of their weight, gravitational, downward gravitational pull, that is the weight of the solid, is higher than the force that is caused by the flowing water. then the particle is not going to be eroded. So these two forces has to counterbalance. They have to counterbalance so that the particles can be in place. So you have to have an equilibrium, or rather, the Ws should be greater than F. Ws has to be greater than F at any given point. So you're at any given point, F is trying to push the particle to move to the downstream. The W weight of the particle is trying to resist due to its own weight. So those two have to counterbalance. So with that kind of explanation, let us look at how that principle or how that knowledge has been used in order to calculate the exit gradient. So I've already said for a specific soil particle, you are going to have submerged weight of the particle and seepage pressure. The weight of the particle submerged is the specific weight of the soil times volume. And if you now apply soil mechanics principles, you can write it in terms of specific gravity, and you can write it in terms of this is not porosity. This one is what? Void ratio. You can also write it in terms of void ratio and the density of water. So when you're doing, already we can see something that when we are working with designing a barrage or a weir, we have also to do some kind of ground investigation, some geotechnical investigation, try to determine the characteristics of soil. What is the specific gravity? The seepage pressure, on the other hand, is given by the density of water times dP dl. The dP is the hydraulic gradient. For safety, therefore, against piping, you're supposed to have Ws is equal at least to PS, or it has to be higher, but for equilibrium purposes, we say it is equal. Therefore, you equate those two, and if you rearrange, and if you equate now those two and cancel out the gamma W's specific weight of water, you end up with this equation. Now, for an extreme scenario, that is when we have the critical hydraulic gradient conditions, we need to minimize. For extreme critical hydraulic gradient conditions, then we are, and if we set this one, if we set this one to be, we set this one to be now equal to the extreme exit gradient, then it is supposed to be equal to G minus 1 plus E. But void ratio is given, you can write it in terms of porosity as given. Therefore, your exit gradient is supposed to be given by G minus 1 into 1 minus N. For safe exit gradient, the safe exit gradient, there is this expression that has been determined, and it has to be minimum. This expression, once you calculate it, it has to be minimum. It has to be minimum. Safe exit gradient, there is an expression that has been developed that is 1 all over pi. Is it n or pi? It must be pi. It must be pi. Just wait a minute. Yeah, it is 1 over pi times lambda. It must be 1 over pi times lambda. Yeah, so we have that expression that has been developed, which we are going to adopt as is. The extreme exit gradient G is 1 all over pi square root of lambda times h divided by d. And h is the difference, is the hydraulic head in the upstream side D is the depth of the downstream cutoff file. It is the whatever of the downstream cutoff pile. Now, remember I said if now GE, that is the one that we have calculated, has to be less than the critical hydraulic gradient that is calculated from up here. So you can always calculate the critical hydraulic gradient based on the characteristics of the material. And remember how we derived this expression. We derived it from, because we balanced the WS and PS. So GE has to be equal or less than IE. If now, and this has already been developed elsewhere, if you set this one is equals to 0, what will happen? Let's say D, the downstream depth of downstream pile is 0. What will happen? If you set D to be equal to 0, what will be the value of GE? Elvis Karumbi. If we put D to be equal to 0, what will be the value of, if we set D here to be equal to 0, what will be the value of the safe exit gradient? Okay, that is Elvis. John Akinyi, if we set D to be equal to 0, what will be the value of GE? If you divide anything by 0, what happens?
It's an error.
It is an error. Yes and no. Joel Thuranira, you get infinity, isn't it? You get 1 divided by 0, it's infinity, and it is massive. It, you know, the value that results is too massive. So what are we talking about? What are we saying? If the downstream pile cutoff is absent, then D is equals to 0 and GE is equals to infinity, and your structure is going to fail. So you have to always have a downstream cutoff pile. So now the question is, how deep is that downstream pile supposed to be? And here we use the Lessig. I hope we will look at canals, because once we do canals, we are going to come across Lessig theory. And according to Lessig, any unconsolidated material, if water is flowing through, it tends to erode until you get to, a maximum depth, which we call a maximum square depth. And you can calculate it. And for rivers having a width equal to Lessig weighted perimeter, the Lessig regime square depth formula R is, and R is the maximum square depth, is given by this Q over F. And if you are doing it per meter length of the river, then you have a small q, 1.35 divided by F1, 1 over 3. So when you're designing a barrage or a weir, what we have talked about, first of all, you need to look at the pressures, because those are the pressures you're going to use in determining the bending moment. Those are usually the bending moments that you design so that you can know the weight of your concrete, if you are going to have steel, so all those forces are the bending moments already that have been calculated. So essentially here, what we have done is to develop the bending moments at key points. Then that is 1. 2, you have to determine the depth of the downstream pile. You also have to determine the minimum depth of downstream pile, and you also have to determine the self-exit gradient. You also have to determine the length, the total length of the weir, including the depth of the other piles. How do you determine that? Lens theory. Lens theory will help you, not lens, but Blythe theory will help you determine the depth of the other piles because you have to make the creep length as long as possible. Once you have done that with Bly's theory, then use Koestler's theory to check pressures, and then do adjust your system appropriately. So this is the method of independent variables, and for whoever reminded me about the class today, thank you, because I really wanted to finish this so that next time we start on something else. I'm going to provide, I don't know, I've already given tutorials, I wonder. I'm going to send tutorials and then you can already try playing around with this. Most importantly is, remember when you're calculating, all this is calculated in radians. All this is calculated in radians. All right, so I want us to end at that point so that I can also now prepare to go and have another physical class with the other class. Not unless you have any question. I'm making an amendment to our tutorial, so I will be sending them later. Someone can remind me later today or tomorrow, and then so that you can already start now practicing with what we have done. Question? Any question? Fidel or Witty? Any question, or you can release me. You can release me on behalf of your class. Are you call? And you notice today I've not taken attendance. Yes. You said, Fidel, you have said you have no question.
Yes.
Okay. So today I've not taken attendance because of that mix-up that we had in the morning. I wonder those who have missed the class what is going to happen, but kindly class, just take them through. Remind them to finish the design of wares and barrages part 2 because we left it at halfway the other time. Otherwise, you have a good afternoon, good weekend. We meet again on Monday online.